Okay, hi again, everyone. So today we're going to finish our discussion of hydrocarbons, covering off the two really major groups that we haven't talked about yet. The first being aromatic hydrocarbons, and the second will be allotropes of elemental carbon. Okay, so kicking off, aromatic hydrocarbons, what do we mean there? We're looking at a specific group that have one or more planar set of conjugated carbons. These are ones that connect by alternating single and double bonds. So if, let's see if we can get the drawing function going. Okay, here we go. So these are the ones that we see drawn all over the backgrounds in movies. Usually as a 6-membered ring. Half of them are conjugated, half of them aren't. Of course, there's no reason that those ones should be the conjugated ones. So we can draw exactly the same molecule, 6 carbons, and just have the other ones with the double bonds. So we've seen these before last term. And where we have one or the other can be representative of the whole molecule. Really, we're looking at a combination of the two. And this, of course, this 6 rings or 6 carbons conjoined in a ring with conjugated bonds is called benzene. We can also represent it, and you've seen this maybe before too, where we've got the 6 carbons in a ring and just a circle drawn in the center. The circle really reflects the fact that all of those extra bonds, so what we show normally as double bonds and single bonds, really all delocalize, or they don't locate themselves on a single atom, but spread around the entire ring into one larger delocalized orbit. Okay, you can see it in the picture here a little bit more clearly, maybe. So we can already see that each one of these carbons, or hopefully you see that, they're also bonded to a hydrogen. So each one of them is bonded to a hydrogen just straight on the plane with the carbon, just as is shown down here in the other pictures. So that means that each carbon is bonded to 1, 2, 3 other atoms with a double bond to 1. So each one is sp2 conjugated, and that leaves this extra p orbital just free hanging out here, right? But instead of that being the orbital and those 2 electrons just sticking next to that one carbon, all of these p orbitals can join or bond together on the top, above, and below the circle. And what we end up with is something that's a lot more physically representative as these 2 rings of electron density or delocalized orbital clouds, where the electrons that would be in these bonds, these pi bonds, are just completely delocalized into these different things. So if we're going to fill in the blanks here, we say the alternating double and single bonds allow electrons to move freely around the ring. So electrons in the conjugated orbitals are delocalized. Okay, important concepts for any kind of aromatic, and in fact for a lot of other conjugated bonds as well. Okay, so substituted benzenes. This is an important class of molecules too. So we have the benzene straight molecule, the regular version. And we already said that these are normally just covered in hydrogens. Again, wherever we don't show it specifically filled in, we assume that there's a hydrogen there. But what if we take off one of those hydrogens and replace it with a methyl group? Okay, so by the naming conventions, this is now called methyl benzene. It's also called toluene. A lot of these substituted benzenes have some historic names attached to them, like toluene or xylene or phenol when we get down into some of the other functional groups. But if we're going to, we'll always accept the standard IUPAC accepted version. So stick with these when unclear. And of course, we can substitute more than one of these hydrogens, right? So let's draw another one. And we'll do a methyl group there, and we'll do another methyl group, and we'll just do the circle notation here instead. Okay, so this is now 1, 2, because we want to keep that number low. We wouldn't go 1, 2, 3, 4, 5, 6. It wouldn't be 1, 6, right? So we're going to keep it 1, 2, dimethyl benzene. And we keep doing that with different versions of the same, right? So draw another benzene. We could do 1, 3 dimethylbenzene, or do them right across from each other. Now we have a 1, 4 dimethylbenzene. And you'll see if we kept going up 1, 5, well, this would just be 1, 3, and 1, 6 is just 1, 2 again. We just rotate them, right? So these are the options that we have, and we can also call them by different names. So instead of saying 1, 2, we could call this one ortho, meaning next to. Meta would be 1, 2 apart. And if they're across from each other on a benzene ring, then they're called para. Okay, so this would be ortho dimethylbenzene, meta dimethylbenzene, para dimethylbenzene. And of course, we could do other constituents instead. So we could do what, like a bromine, and a what? Ethene, propane. Okay, so this would be like 1 bromo, 2, 3 ethyl. No, I said propyl, didn't I? Let's go up, erase that. All right. 3 propyl benzene. And just for completeness sake, we could say meta, okay? So there, and we're going to get to other functional groups that we can add onto this thing. Really, the options are endless. And before we get away from just a single benzene ring, I also want to point out there's if we had just an aryl group, just a regular, what do we got? 1, 2, 3, 4, 5, 6, 7. So this is be a heptane. And we had a benzene ring attached to this. Okay. There we would call it a phenyl group. So wherever you see, again, kind of if you're looking around the house and just want to check on the back of your shampoo bottles and things for some of these long names, if you see anything with like a phenyl, so like a dimethylphenyl, let's put a couple of methyl groups on there. So this would be, what, we'll say it's 1, 2, 3, 4, 5, so 3, 5 dimethyl 2-phenyl heptane. That's how that would be described. Okay, so let's get on to, so another class of aromatic hydrocarbons are the polyaromatic hydrocarbons. So this would be where we write polyaromatic hydrocarbons. And these are where we combine more than one aromatic carbon ring at 2 adjacent points on the ring. So we're just going to stack rings together. So we could keep this going if we wanted to. These are usually something like naphthalene, I think is one of these. So it can be still aromatic, still quite flammable, but potentially also seen as a solid or a liquid at lower temperatures. Which is why we use some of those materials, say for starting fires and that sort of thing. What else do we see? More aromatic carbon rings. A lot of actually drug classes will have a couple of aromatic rings attached to each other. Steroids comes to mind, where you can see something like that. I'm drawing it badly, but you get the idea. This is supposed to be a pentane or pentene ring. Okay, but they do show up quite a bit. Okay, that's all I wanted to say about fused ones, except for, yikes, I'm going all over the place on this. Except for, okay, elemental carbon. So, I don't know if we talked about in class, I don't think we did, but different forms of an element can also be called different allotropes. Okay, so in all of these cases, it's just carbons, but they're arranged differently, or they have different hybridization. They're bonded to a different number of carbons each. So even though it is still just elemental carbon, it's still a different, different molecule, different reactivity, different behavior. So the main one that most carbon on Earth is found at is just graphite. Graphite, which is this guy right here. So stacked layers of fused benzene rings. So these are aromatic hydrocarbons, more carbon than hydro in these cases, where it's just sheets and sheets and sheets of stacked layers. Interestingly, people have been doing this a long time, but we only just recently realized that we could delaminate some of these layers and just pull off a single sheet of these fused benzene rings. So this is called graphene. That's an E-N-E. And honestly, there's so much interest in this material as a 2D material that we really could do a whole course on just 2D carbon materials. And especially if we have them just in one layer, these are atomically thin and atomically flat, smooth surfaces that we could put, say, locate some hydrogen gas on if we want to use that for a reactive surface like we saw with the hydrogenation. We can store other gases. We can do other chemistry just on the surface there. A really interesting thing that if you're interested more in the electronics and physics of it is to look up what happens when you lay just two graphene sheets on top of each other and twist it at just a very slight angle. So I think the angle is about 1.1 degrees. And suddenly you get some either, say, semiconductive or even superconductive properties out of these flat graphene layers. Other shapes that graphene can take, so this would be a tube. If we look, there's an opening right at the front here. We can get different diameters or internal radii on these. We can also have single or double wall or even multi-walled carbon nanotubes, which is how we'd call that. Really promising material too, mostly now just kind of thrown into other materials as a hardener. You see it in tennis rackets and shoes and that sort of thing, where it's not really doing the job that it could do. It's, I think, like even thinking things like water filters. So water as a molecule is smaller than this diameter generally. And this, of course, is a polar molecule. This would be a non-polar or hydrophobic interior surface. So if water gets pushed into here, it wants to come zipping out the other end just about as fast as it can. And if we decorate the opening here with the right kinds of, say, functional groups, which is what we're going to talk about next, water will be collected in, but other contaminants, larger things, even as small as virus, could be left behind, or just proteins or anything else. Yeah, and so C60, if you get 60 carbons to arrange themselves in just the right way, actually just the right way is the same way as a soccer ball. If you colored some of these in, it would look exactly the same. See, one down here maybe. It's also called a buckyball. or Buckminster fullerene. Buckminster fullerene. After Buckminster Fuller, who made this geodesic dome in a building before we found it in the molecule. Okay. Also quite interesting for properties, thinking about caging other molecules in there or how they interact on the surface, because there is some surface tension here on the carbons. Could go into more detail, but again, I think this is one that if you're interested in, look it up. So diamond is another allotrope of elemental carbon, because it is just carbon. But instead of being sp2, these are all sp3 hybridized. So every carbon is attached to another carbon. And it's just stacks of carbons. All bonds are at 109.5 degrees in a tetrahedral kind of arrangement. So as opposed to, I didn't even mention that, but up here, say the graphene or the carbon nanotubes, because these are all conjugated bonds, they'll conduct electricity, or if we take it at the right angle across the sheet, they can be semiconductors, because electrons can delocalize across the surface there. But when they're all sp3 hybridized and all of the electronic density is localized to a single atom, then we lose that conductivity. So that's why diamond insulates, where other carbons can be conductive. Okay, so that's going to do it for today. We'll pick up next video with other functional groups, and we'll start talking through how some organic chemistry gets done between those functional groups. Okay, as usual, thank you for watching, and we'll catch you next time.